Hi, this is Tim from Tigra Astronomy, and I am just making a video to show how we plan and schedule observations on the Automatic Observatory. Now, I've had an email today from Dirk Freubrich, who runs the HOYS Citizen Science Project, Professor Freubrich at the University of Kent, and the email we've had from him, let's just skip across onto my screen, and the email we've had from him is to say that they've identified a potentially interesting target, V1491Cyg, that's variable star 1491 in Cygnus, and I've posted this email up on the Facebook group, the Moncton Stargazers Facebook group, but basically they think that it might have a 180-day period, or it might have a 580-day period, and they're not really quite sure which it is. So they want us to observe, particularly between the periods of 12th of April to the 10th of May, which is a 2-week window when they think there might be an eclipse of material in the accretion disk passing in front of the star, so the brightness would drop a bit. And they also want us to observe 27th of June to 25th of July, and the data from these two batches of observations, they hope, will enable them to determine whether there is in fact a 180-day or a 580-day or something else or nothing at all periodicity going on. So this good stuff, science is being done here, right? So so we need to put that into the observatory. So the program I like to use for this is called AstroPlanner. Now, it's not the most popular choice I've seen, but AstroPlanner does have some redeeming features that are quite useful for this sort of thing. Now, I've actually already got the observation entered in here, but I want to show you how I got to it. So the first thing is I'll put V1491Cyg in as an object, and we can look that up on the sky. And this is actually one of the weaker features of AstroPlanner. It's not a massively feature-rich image of the sky here, but it's usable, and you can see here in pink where the object is that we're interested in. And right now it's about 11:30 in the evening, and so the object's risen above the horizon, and as the night wears on it will follow around the declination lines here. So clearly, let's just step a few hours into the future here. So this is 4:50, that's UTC, I think. Let's look at UT, that's 3:50 UT, and that's okay, so looking at 0450 universal time, the object is starting to get up high enough where we can image it. So if I just switch back to the Objects tab, there's a couple of things here. Let's just unfix the date and time so that we see a proper view. And I'm just going to magnify the screen here so we can see what's going on. So in AstroPlanner we have these graphs here. So if I've got that object selected, it goes and scrolls it off the screen for me. Just bear with me while I grapple with the magnifier. Okay, there we go. So this graph here is the short-term observability graph. So this is one night. So this is daytime, and then coming through into twilight, civil twilight, nautical twilight, astronomical twilight, and full darkness. And then this is twilight in the morning, and it's dawn, and then into daylight. So you can see the white line here represents now. So the object is the series of red crosses here, and as you can see it's quite low down on the horizon and getting higher and higher as the night goes on. And then this purple line here and this purple curve, this is the observability curve, and this vertical purple line here is the maximum observability, the time of maximum observability. So this object is best observed right before dawn, and sure enough, in the email it says it's a morning object. So we, I guess, want to be observing this object sort of in the wee hours of the morning through till dawn. And so this is a really, I really love this feature of AstroPlanner, because you can see at a glance, you know, when things are going to be observable. So the other aspect to this, let's just come out of the magnifier. We can look at the field of view. Now in the field of view screen, we've predefined the equipment that we use. So the telescope is the LX200 12-inch Schmidt-Cassegrain, and the STXL 6303 imager in here. And we can pull down this thing here and say use the field of view for the equipment you've specified, and that will calculate and display what we will actually see through the telescope. So here we go. So I'm just going to set this to 0 for a moment. Now you can see that the program has downloaded several images of the Pelican Nebula area and overlaid them for us over our field of view. And the object that we want to observe is the red thing here. So V1490Cyg, there we go, 1491Cyg. And this target down here is the HOYS118 target, which is the pre-existing Pelican Nebula target. And I'll go into this one in a moment, but basically this is the thing we want to observe. Okay, so now the Automatic Observatory, if you want to take long exposures, and we will be taking 5-minute exposures here, you need to guide the telescope, and in order to do that you need a bright star on the guide camera, and I covered this when I did a talk on the Automatic Observatory some months ago. And so really the whole thing driving how we frame our image is the best guide star we can get. And although so this red rectangle here represents the field of view of our imaging sensor. So this is the thing, this is the picture we will take. The little square at the top here is our guide chip, and that actually sits out in front of the filter wheel. So it's not affected by the different filters, and it's offset from the main imaging chip, which is why it's off to one side like this. And we can rotate this around using our instrument rotator, which is why you've got, and they're actually difficult to see, but in fact they're not showing up. There should be a set of dotted lines around this image that show you the annulus around the main chip, where you can see where there are guide stars that you could use. So although there is a little guide star in there at the moment, if we hover over that and then look down at the bottom of the window, it appears just here, but annoyingly disappears when you move the mouse away. So if I hover over that star again, and you can see the information pop up there, that star is magnitude 9.24, and which is okay. We could guide on that. But well, really, the brighter the guide star you can get, the better it is all round, really. And actually hiding down at the bottom here, just under this key, this constellation image here, is a really, really bright magnitude 5 star. If we could get that in the guider, that would be super. So if we just rotate the field of view by 180 degrees to start with, and just wait for it to recalculate. Now you can see up here is this really bright guide star, and that is, yeah, magnitude 5.06. So we'll be able to really get the adaptive optics locked onto that star and guide really quickly. So, but it's not on the guided chip. Now we could rotate until it sort of comes around here and then nudge it down a bit. But I don't like rotating the camera other than on 90-degree intervals, because the guiding goes a bit, it's not very good unless the camera guider axes line up with the telescope axes. So for the time being, I'm restricting myself to 90-degree increments of rotation, which is why I used 180 degrees there. So nevertheless, that guide star is not in the box. So what we can do is just click on it and drag it into the box, into the middle there. And then once that's recalculated, you can see the image is reframed, but we can still see the thing we want to image under here. So we're okay. And you can now see what this target in the middle is, because I've actually created a new object called HOYS118-guided, and that's it right in the center of the crosshairs there. Let's just zoom that a bit. I've actually already created that object, and so as to align that really bright guide star right in the guide chip there. So here's one I prepared earlier then, HOYS118 guided, and the coordinates, if you look at the coordinates of V1491Cyg, it's 2051.04 and 4423.50, and the object I've created is just slightly different. It's 2050.07 and 4423.41. So the coordinates are a bit off from the target, but we have to do that in order to get a guide star. That's critically important because of the way our optics work. Okay, so having got that, I can just move that over onto my other screen over here so I can refer to it, and we can open up the observatory. Now I'm using a web browser and I've logged into the observatory, and excuse the noise, there's something in the kitchen going off. And okay, so the observatory's sleeping at the moment, and here's a thing it took earlier tonight, which is one of the asteroids we're following up, and that's come out quite well. And so we can just go into the single series menu item here and create our object. So you can see I've already run through this once, and so these should all be right, but we want to create a new observing plan, add it to our UKC HOYS CAPS project, and it's going to be called HOYS118. The coordinates 2050.07, and these are the coordinates that we down here that we derived from Astroplanner, and 4423.41, and the position angle is 180 degrees, which rotates the camera 180 degrees to put that really bright star in our guide chip. And then we're going to take a series of 4 images in the red filter, the green filter, the blue filter, and the hydrogen alpha filter. And we're going to take 300-second images each time and use binning 2x2. Now, binning just takes the okay, so unbinned images uses the full resolution of the imaging chip. So every pixel on the chip produces a pixel in the final image. Now, when you bin 2x2, you take 2 pixels across by 2 pixels down, so a total of 4 pixels, and you add the value of all those pixels together, and the total of those 4 pixels produces 1 pixel in the final image. So the resultant image is a quarter of the number of pixels. It's half as wide and half as high, so a quarter of the number of pixels. But all of the pixels in the chip are added up and put into the target image. So the reason we do that is because the pixel scale, the smaller your pixels are, the more critical guiding is. And you need, with a really high resolution image, you need really, really good tracking on your telescope. And the one we're using it's an okay mount, but it's certainly not superb. It's sort of in the late 1990s, when they became popular, they were actually really quite good telescopes, but by today's standards they don't track very well, and even with the adaptive optics that can be a little bit problematic. So we have to drop down in resolution a bit, which means that our guiding isn't quite so critical, and also we can get a brighter image with a shorter exposure. So it's really quite good. We really need a focal reducer on the system, but we haven't got one, so we have to bin. And so we're going to do these 4 images. I won't go into dithering. That's something to do with how you reduce noise in the final images. And then we need to set constraints for our image, i.e. when can the observatory observe it. So we need it to be some way above the horizon. So normally this defaults to 35 degrees, but I checked up in Astroplanner, and it doesn't actually get that high in the sky. So I needed to drop this a bit, otherwise it's like an hour before dawn before it gets high enough to even start observing, and then it doesn't leave very long to take the images. So drop that down to 25, and then we've got a moon avoid constraint. So this means that the target must be 120 degrees from the moon when the moon is 14 days old, so full moon. So basically, if there's a full moon, the target's got to be 120 degrees away. So that either means right across the other side of the sky, or more likely it just won't happen that night. So, and we want the sky condition to be at least good. So the options in here are excellent, good, and fair. And there's also a poor, but I guess that's no constraint at all, because the sky can't be worse than poor. So we want it to be at least good. Priority and series, I'm giving it a fairly high priority, 99, so it will image before some of the other plans. And we're going to repeat the entire series 8 times, so that will actually get 8 reds, 8 greens, 8 blues, and 8 hydrogen alphas. But the sequence that will happen, it will do 1 red image, 1 green, 1 blue, 1 hydrogen alpha, and then go back and do the second set, so another red, another green, etc. And Dirk suggested this to me. Rather than doing a batch of reds and then a batch of greens and then a batch of blues, it's better for the science if you interleave them like this. So do 1 red, green, blue HA set, and then go back to the beginning and do another set, and just do that for an hour or 2 hours. And for reasons I don't fully understand, it's better for the science doing it that way. Excuse me. Okay, so we're not going to space the images at all. We just want to rattle them off as fast as possible. And best efforts here means that if the series gets interrupted, say by sunrise, then the plan will just stop and be deemed to be successful. Even though it's stopped, it won't fail for that reason. So we're going to enable the requests immediately, but there's some more stuff here. Okay, so the monitor interval is 3 days. So we're going to try to image this target every 3 days if we can. Now, weather in the UK probably won't allow that, but that's our ideal situation. And we want to keep that 3-day cadence up until the 10th of May, which is the first observing window. So if you remember, the email asked us to observe from, I think it was 12th of April to the 10th of May, something like that. Well, I'm not going to put a start date on it. I'm just going to say, well, start immediately if we can. And we're enabling the request immediately. So the scheduler, having submitted that request, which I've just clicked, successful. Okay, so we can go and we can go into the schedule browser and way down to our UKC HOYS CAPS project here, and HOYS118, there we go. And there's our plan, and here are our image sets. So red, green, blue, HA, and 300-second exposure, binning to 1 off, dither. And if we look at the top level item here, you can see there's a repeat count of 8 here, so we'll get 8 repeats of each of these. So here are our constraints: sky condition good, and that's great. I'm going to actually increase the priority of this to 999. The reason I didn't do that is there's a bug in the web form that only lets you go up to 99, but you can actually put any number you like in here. And must run after now. Let's put that in even though I didn't enter anything. Save changes. Okay, so this is active on the observatory now, and if we look into one of these, you can see its status is pending, which means it's eligible to be run. And the reason it's not running at the moment, I think, is because the observatory is closed because it's cloudy. And if we look at the Skynet weather system, you can see it says unsafe, 60% cloud cover, and so it's not safe to observe. So as soon as there's a clear sky, maybe even later tonight, if it clears, the observatory has already taken some asteroid observations tonight, which I didn't expect. But if it does clear up, it will just open and start taking the images. So all we can do now is sit back and wait for the results. There will need to be some flat fields taken to match the images, which is something I'll have to do manually. But I'll let you know when anything happens. I can't wait. So I've been Tim from Tigra Astronomy. Thanks for watching, and good night.